Nej, no, if Nej says we should get started, we should get started. All right, so today I have Sebastiano. Sebastiano is a postdoc fellow here at CITA, and he's on the prestigious Humboldt Fellowship, visiting us from Germany. He's going to be here for the next year or so, so you'll have plenty of time to chat to him if you don't get around to chatting to him today. He's working within the plasma astro group, and he performs his astrophysics through the lens of observation. So, I would say much closer tied to the astrophysics than I. He is part of many observational collaborations like Gravity, which I'm sure he'll talk to us a little bit about today, perhaps. He completed his PhD in 2021 at Max Planck Institute for Extraterrestrial Physics at Garching with his thesis, Probing the Physics of Accretion Flows of Sagittarius A star. So Sean will be very interested in this, Sean's online. He's now an expert on all things Galactic Center. And interestingly, Sebastiano has his master's in both astrophysics and biophysics, which I found out today. So he's also our resident CITA medical doctor. Please see him for all your queries about rashes and bruises. Just kidding. So today he'll be talking to us about infrared observations. What was that, sorry? The resident CITA medical doctor. He's not a medical. No, the biophysics is true. He has a biophysics master's.
I don't have a biophysics master's. I started biophysics, but I never completed it.
Okay, well, it's on your CV, Sebastiano. You may have to admit
I
it.
started it, I didn't say I finished.
So today he's going to be talking to us about the infrared observations of the Galactic Center. Let's give him a warm welcome. Take it away.
Alright, so yeah, this is a talk about infrared observations of the Galactic Center. Some of you have heard parts of the talk in here and there. Just bear with me through the parts that you've heard already. So starting off with a definition of what Galactic Center means in this context, when I talk about the Galactic Center, it's everything within the sphere of influence of Sagittarius A star. That's very important to say because people will say the Galactic Center, they mean everything essentially that is somewhat close, within a couple of kiloparsecs. This is a view of this 30 central arc seconds, which is roughly half a parsec, give or take a bit. And in this picture you see a lot of stars. You see roughly 10,000 stars that sort of glow like point sources here. You see a lot of gas, and this is this extended structure that you see here. And then of course there's a lot that you don't see, because between us and the Galactic Center there's a lot of dust which blocks the light. That's also the reason why we look at this image in the near infrared where the dust becomes more opaque, and there's that distinction. When people talk about dark stuff, they think about anything that is probably not ordinary matter. Just want to point out that we see 10,000 stars, but this is the top 2% of the stellar population that we see. So we see mostly giant stars in these pictures. Anything on the Herschel-Russell diagram, it's on the giant branch, and the asymptotic giant branch, and O and B type stars.
How much gas associated with individual stars? Gas you pointed out?
This is like free-floating gas, and these like dusty-looking or like reddish stars, they are either, I'll get to it, Wolf-Rayet type stars or giant stars which have high winds, and what you see here, the long wavelengths, is this wind stellar ionized emission. Then just to train your eyes, this is this like little crown that you have here that goes down, and Sagittarius A star sits in between those down here. So as if you draw like a finger, just sort of put like a triangle, and then we'll find the rough position of where Sagittarius A star sits. You'll get to it once you work on this a lot. The reason why we know Sagittarius A star exists is mostly because of long-time observations of exactly this field. And in particular, of course, this video that you might have seen or might not have seen before, which is a series of images taken from Paranal, which tracks the motion of stars around Sagittarius A star. This is the star that's called SO2 or S2. It goes around Sagittarius A star on an orbit of roughly 16 to 18 years. Well, we actually know very well how long the period is, but 16 years roughly. And from that you can fit just a capillary orbit to it, and you get the enclosed mass within this orbit that you saw before. It's roughly 4 million solar masses. And the best hypothesis is that this is a compact object. This is, of course, what won Rainer Genzel and Miriam Getz the Nobel Prize for the discovery of compact objects in the galactic center. Now, what you see here is a zoom in further, where we take a better telescope, which combines the light from 4 telescope. We build an interferometer, so zooming at a higher spatial resolution. You can track really the central light now, so from here. You can see like there's daily motions of stars, and in particular, you also saw like one thing that wasn't moving, and that is Sagittarius star and its counterpart in the infrared. So another take-home message is that in the near-infrared, Sagittarius star looks like sort of a B star. It's really faint if you think about it. That this is a compact object of 4 million solar masses, but sort of the thing is that like the bigger star is sort of its near-infrared output. Of course, you can make simulations of accretion flows, but the HT has also imaged the really central region around Sagittarius star. Now we've zoomed into from something that was around, a couple of milliarc seconds to something that is roughly 50 microarc seconds, so factor 100 more spatial resolution, and then you see sort of this glowing little thing there, and that is, of course, the central region around Sagittarius star. So the first part of the talk is going to be about the stellar population. From the stellar population, we move forward to accretion onto Sagittarius star. So for the first part, we'll talk about a peculiar population of stars that has sort of been one of the main research topics on galactic center science, and this is the so-called young stars in the galactic center. So why do we call them young? This topic came up in the 90s, where people were for the first time able to see individual stellar sources. So a couple of point sources, when they took spectra of the sources, they saw this broad emission lines. If you look at the kilometers that you see here, so kilometers per second, these lines are thousands of kilometers, like roughly 1,000 kilometers in width. It's of course peculiar, that's almost at the rotational rate of speed of any star. So this was very positive. What did Burst were in the first place? After some time, they realized that these emission lines correspond to the spectra of so-called Wolf-Rayet type stars that had been discovered a long time before in different frequencies. Now this is a picture of a nearby Wolf-Rayet type star taken with WSD, where you have the central point source. This is the actual Wolf-Rayet type star. And you also see this gas structure that sort of seems to blow away from the star. And this is the region for these very broad emission lines. You have the central star that is very hot, very close to its hydrostatic equilibrium, blows off a lot of stellar wind. The stellar wind is being illuminated and shines, really emits the light in these very broad emission lines. Now, if something is very bright and it's a star, that means it must have a lot of mass. If it has a lot of mass, it will eat up the mass very fast. So these Wolf-Rayet type stars, they don't live very long. So the max they live is something like 10 million years. That must mean that they must have formed very recently. And that is very perplexing, because if you think about star formation in anywhere else than the galactic center, it kind of happens like this. You have giant molecular clouds, sort of fragments, and stars form in these figures. Now, imagine putting a supermassive black hole in this giant molecular cloud. It is, of course, going to stir up all of the gas, and it's completely destroy sort of your plastic star formation channels. So, puzzling, how do you get to form stars in this region? The answer to this question, or one of the best clues that we have how this could form, lies in the velocity or the kinematics of how these stars move around Sagittarius star. So let's dive into this a bit more. When we look at the galactic center, there's of course a lot of stars, and if you just look at the picture, there's no way of telling what the age of the star is. For this you need the aforementioned spectroscopy, so you can look at the spectroscopic features and decide sort of what spectroscopic classification you need. We've now covered roughly 25 to 25 arc seconds of the central region with a technique called IFU, integral field spectroscopy, where in each pixel we get a spectrum, and that allows us to tell this star has this spectra, this star has that spectra. And with that, we've identified roughly 200 young stars in the galactic center out of 10,000 bright stars that we see, giant stars. Now, for an individual star, we get relatively easy the position. So we just take an image. You have to think a lot about coordinate system, but once you figured out how to make a coordinate system in a stellar field, you sort of have the point where it's at a certain time. These things move quickly, but not that. So we have a linear motion on the order of time to year scales with an 8 meter plus telescope. You can, for any of these sources, pretty much measure a decent projected velocity. What you don't have, other than in the central region, is that the star curves towards the black hole. You do not measure acceleration. So you're sort of stuck with projected motion on the sky. And lastly, of course, if you have the spectra, you get the spectral lines. You can look how these lines are blue or redshift with respect to the central frequency, and you can measure sort of the projected radial velocity. For anything that doesn't have an acceleration, you do not measure the depth. So you're sort of 5D constrained, but your depth information isn't there. So if you wanted to calculate an orbit, well, it doesn't really work. You have to guess the depth. But there's good ways to guess. You can say, well, it's just bound to Sagittarius A star. You can take priors on the allowed accelerations that the star could have, or you just say, well, it's Gaussian. Also works. And then you sort of fill up your 5D space. You have the set coordinate as well. And then you can calculate for a given black hole the posterior angular momentum distribution for an individual star. Now, if you just look at one, it's going to have a blob somewhere in the sphere. This is just, your world map, latitude and longitude, so it's a 2D projection of the sphere. If you have multiple stars and they happen to have the same angular momentum, you start to get clusters. And of course, this sort of looks like a stellar disk. Now, if there was more than one stellar disk, we'd find another blob in the sphere, and now if this blob was somehow radially dependent, you could turn off and on those blobs in your plot by binning your data up radially. So let's exactly do that. Let's start with the first arc second to the second arc second. So this is sort of this region, excluding now the central arc second. What we see is this very coherent motion in the young stars. This is the so-called clockwise stellar disk. It was discovered in 2003 by Hugh Levin and Andrea Belladonna, I think, while they were here. So neat little history fact. In this sort of clockwise system, you just have to believe me that this direction means it's clockwise on the sky. Starts to fuzz out if you sort of start to move further. So it's not that coherent anymore. You see just this tick up here, and especially once you go to like this projected motion from 4 to 8 arc seconds, you see that what had been the clockwise disk sort of disappeared. This was argued to be a warp of the clockwise disk system. And this was something that was fought over very hard in the last 2 decades. I think we've sort of arrived that this feature is real, but its significance is relatively low. It's around 3 sigma, so you can sort of argue whether it's real or not. Once we start to look at the further away stars, so let's take a look at these things, we see that the angular momentum sort of changed its direction. There is one very prominent feature here, and maybe 2 more blobs here. So this is really a new stellar system that is at larger distances from Sagittarius A star. And well, if you look at the largest radar, we just don't have too many stars to say much. But so the system that we're looking at, the young stellar system, is going to be schematically looking at this. We have this very nice coherent system in the central arc second, reaching up to say 4 to 6 to 8 arc seconds away from Sagittarius A star. And then you have definitely another system that I call like filaments that are further away. Now, typically in the Galactic Center, things are relatively disputed, but we've just had another paper came out last year that confirmed this discovery. That came out from the UCLA group, and they sort of saw the second angular momentum feature as well in their data, which is sort of the best confirmation of anything we can have in the Galactic Center, so that's relatively neat. Okay, so now we are looking at sort of excluded the central arc second around Sagittarius A star, and here you have orbits properly measured. So if you look at the clockwise system, that sort of looks like this for a couple of the stars, we can properly track out the ellipses. Once we zoom into the central arc seconds, the kinematics of the system completely changes, and you get something that looks like a bit like like a nucleus in some sense. And the stars completely, their angular momentum is completely destroyed. There is no more disk, and you get this isotropic distribution of stars. Now, An isotropic distribution of stars close to a supermassive black hole per se isn't surprising. What is surprising is that these stars are relatively young, and we don't know of a dynamical mechanism to destroy angular momentum so quickly. So angular momentum is conserved. There's processes, just think of the simplest one, which is two-body interactions. They have a certain time scale for which it takes to sort of remove the angular momentum and drive the system to something that is isotropic. In the case of the Wolf A-type stars and B-type stars, they don't live it long enough for this mechanism then to work. Because one of the long-standing theoretical puzzles that we have is how to make this. Solutions could be like the Hills mechanism, that you have binaries that are bound, or is ejected, but also this has problems because you're detecting much more eccentric distribution than the one is observed. So yeah, there isn't really a solution to this problem, but that's pretty good. Like there is no doubt that they are in this configuration.
Are the two rings co-equal?
It's not something we can say very well, because for dating the stars, you need very good spectra.
But these are young stars. Huh?
They're young stars, but there are some Wolf A-type stars in the disk. Those can't be very long. So I would say yes, but there's also a lot of B stars. So you could have random association of a Wolf A-type star with that kinematic feature, that's just a chance thing. And the B stars could be like 50 million years to 100 million years. So we can't really say. I'd say it's plausible that they're the same.
50 million years is young. Yeah, I can see.
It's still young, but you would have two star formation events, so the different angular momentums would be more trivial to explain.
Right.
So how does this relate to how the stars formed, and why did I say in the beginning that this kinematic sort of gives us a picture of how the stars are going to form? The idea is that however you do it, you need to have gas fall onto Sagittarius star. It needs to be in there first place. So one reasonably motivated picture is that you have gas structures around Sagittarius star that we see called the circumnuclear disk. Within the circumnuclear disk, you have two gas clouds that sort of bump into each other, lose angular momentum, and start to accrete, or any other way of making gas fall into Sagittarius star. Now, in this one simulation that I cherry-picked from Hobson reaction, the simulation sort of predicted a picture that would go like this. You have them collide, they start to fall into Sagittarius star. A central accretion disk forms, which will correspond to this picture here. And there's also gas streamers that remain in larger radii. And in their description of how star formation works in accretion disk around supermassive black hole, they saw that stars are formed both in the stellar streamers and the central accretion disk, and I find sort of just visually very pretty compared to the observations that we see. There's another paper by Yuri Levin that came out last year, which has another very intriguing idea, is that in principle, he argues that you don't need like complex star formation. You could just have a singular accretion disk that would in this case be in the accretion disk of the further out filaments. And then because the overall star cluster has a net angular momentum, you get a torque on the stellar disk that is stronger the closer in you are, and you distort sort of the inner disk to align with the net angular momentum of the star cluster. So dynamics question how reasonable that is to really explain everything. I think it's a very good picture because it explains this change in angular momentum. And we do see that the clockwise system is relatively close in angular momentum space to the net angular momentum of the underlying stellar cluster.
The inner part is torqued into the cluster direction, not the outer part?
The inner part. Like, I mean, everything, I think, but just in terms of time scale, the inner part goes faster. So you see first an alignment of the inner disk, and then this cluster sort of rips apart. And you get like an outer ring, which still has the angular momentum from the original disk, and the inner part started to align with that. He's done that in simulations, I think,
Sure, right.
Yeah, look, for me, it looked very convincing. I'm quite happy with the Okay, so I promised to go from stellar dynamics towards accretion onto Sagittarius A star. The young stars play another role, so we can have a little intermediate step going from the disk from young stars to Sagittarius A star. When you look at the gas distribution in the galactic center, you saw this big structure that you saw before. This structure is on a stable orbit of a couple of thousand years. It's not going to fall into the galactic center anytime soon. There's no reason for it to fall in there. It's just on a stable planetary orbit. At the same time, you have these wolf-type stars that blow a lot of wind. And now Sean and Diego Calderon and Jorge Quadra have been leading a lot of work where they simulate the stellar winds in a realistic simulation of the galactic center, and they can show that under certain assumptions, they can really make this gas fall onto Sagittarius A star, and then you form an accretion disk, and so here's an angular momentum to carry from the clockwise system from where the gas is launched. And that sort of also explains the EHT and gravity observations that do have a measurement of the line of sight of sort of the angular momentum of the accretion flow, and those two mesh together. I'll get to this in a couple of slides. Now, however this gas reaches the galactic center in the near infrared, a typical observation, so this is a Spitzer observation of 24 hours, sort of looks like this. You have some low-level variability, and then you have these big bumps in the light curve. And these big bumps in the light curve we call there. Just as a warning, this is a phenomenological definition of what a flare is. We just look at it, we define the beginning and the end. A problem, for instance, is this a singular flare, or is this three flares? Is this double peak, two flares that overlap, or a single one? There's a good answer to this. It's just something that we have to take as an observational fact in this framework. If you take this light curve and you turn it into a flux distribution, you get a measure of how bright Sagittarius A star is at one frequency at a given time, and this is sort of the flux distribution in the near infrared there. So on average, Sagittarius A star in the near infrared is factor 10 fainter than it is in the radio. So this is at 220 gigahertz roughly, so when the EHT observes, and then most of the time it's a factor 10 fainter. When you get these bright peaks in the light curve, flux goes up and can become as bright as Sagittarius A star. Again, this very bright flux here is a B-type star. Down here it's B9 or A-type star, so pretty faint, 70th magnitude. When we measure the spectrum between two wavelengths in the near infrared, it's really hard to measure it down here at low frequencies, but at high frequencies, what we seem to always see is a rising spectral index of roughly 0.5, so the flare seems to go up. And sometimes we have X-ray counterparts which have a falling spectral index. So from this we can try to model the physical conditions in the light that we see. And this is a typical observer model of what makes the flares. So here just a temporal evolution of one of those things that go up and down. You have red to blue, this is temporal evolution. This one lasts about 40 minutes, we define. You see this rising spectral shadow, and this falling spectral right there. One thing we saw in this particular flare was that the near infrared was relatively bright, and the X-ray was relatively faint. So there wasn't a clear way to sort of connect the near infrared and the X-ray through something like a cooling break. Typically, this would be synchrotron emission, and many flares that we've seen before had a falling spectral index that corresponded to a classical synchrotron cooling break of -1 between the two. In this one, it was actually too faint in the near infrared, which is why we said, well, we just cut off our electron distribution at an energy corresponding to the X-ray, and then we do have the energy, the maximum Lorentz factor of the flare constraint, landing at roughly 10 to the 5. This is relatively simple modeling. One thing that this modeling cannot do is tell you the magnetic field strength independent from the size of the emission zone and the number density of the emission zone. This is just a synchrotron block. You have to assume one or the other to sort of match this. And there's no way to get this to generate. There's You cannot measure how big it is. You don't have the spatial resolution to resolve it, and you don't know how dense it is. Okay. This will become important later on, but we can do more things than just measure the flux density of the spectrum of the flare. We can also, with gravity, measure the position of the flare on the sky as a function of time. What is important and you should take home is that gravity doesn't have the spatial resolution to resolve the emission zone of the central region like the PhD, for instance, but it can do astrometry relatively precisely. So all you can do is sort of take a look at where the light is as a function of time and attract. This is exactly one example of a flare. It went around in roughly half an hour, like an hour or so, and it makes this beautiful ellipse. Gravity's observed multiple flares by now. I think we have astrometry of 5 flares, and this is the phase-shifted astrometry of all those flares, and you can see it tracks nicely this sinusoidal modulation. Gravity not only can measure position as a function of time, it can also measure the linear polarization. And if we look at the linear polarization, we similarly see such a wiggly line. I'm not an expert on how to do the polarization modeling, more on how you measure it. But if you put a simple model to it, where you have a glowing sphere with a magnetic field threading in it, you ray trace this single zone thing going around a black hole. You can model, I think there's this black line here, or maybe it's not this black line here, I don't remember. You can model the both the astrometry and the polarization of the sphere, and you get out sort of the orbital radius and the inclination of which view. The radius is relatively trivial to sort of guess from the astrometry. The orbital radius is not so trivial, I think, or it's actually similarly trivial. You just look at this, it's relatively round. If we were looking at it in more adjunct configuration, you see a single street. Is that clear? Is that a good explanation? And then lastly, I wanted to get back to this aspect of the magnetic field in the emission zone that was unconstrained from our modeling of SED modeling of flares. And one clue to solve this is through measuring the spectral index as a function of time. Now, in the near infrared, we are sort of limited to instruments that can measure the light at different frequencies, but we might have other shots with other instruments. And one particular regime that comes to mind is the mid-infrared, which so far had no detection of Sagittarius star. In particular because in the mid-infrared, the galactic center looks like this. So you have again this very broad streamer, and this is at 8 microns, so you're mostly looking at dust emission. But what you do not see is Sagittarius stars. And the reason is that the galactic center is so bright from this thermal dust that you see, a couple of hundred Kelvin here, it completely outshines Sagittarius star by a factor 100 to 1,000. So any ground-based observation sort of lacks the photometric stability to subtract out this foreground emission and get to the variable emission of Sagittarius. Now JWST solves that because it goes into space and there's no more annoying atmosphere. And this is what JWST observation of the same field look like. If you look at this, first you see the dusty structure in here. You have sort of the cutout where we subtracted the median image, and you see that during the time when the time curve down here goes up, there is a point source that peaks up at 4 different wavelengths. So another neat thing about JWST, it exactly does this multi-frequency observation in a single instrument on a single platform, so you need a lot of constraints on the spectral index. Now, focusing on the light curve again, the flare looks pretty normal if you compare it to the ones that you saw before. Flare goes up, you have the first peak, goes down, 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 and then the third peak in this first channel is smaller than the third. If you look at the longest wavelength, you see that the first peak is actually lower than the third. And this is exactly this thing that we were looking for, this change in the spectral index that will give you an independent constraint on the magnetic field configuration in the measure. Now let's put these together. Let's just normalize everything, then we don't have to worry about extinction or anything. Just make this around 0, first peak around 1, and you see exactly this change in the color as function of wavelength here, coded red to yellow to red. If you make a log plot and you measure the spectral index between wavelengths, you see that it exactly has this change of minus 1.5. If you're familiar with synchrotron cooling, minus 1.5, of course, is the telltale sign of that. You also already see timescales happens on 30 minutes. You just take this, take the observing image, and then you get an observing wavelength, and then you get an estimate of the magnetic field just simply from synchrotron cooling timescales, puts you on the order of 40 to 70 gauss. Now we can do this a bit more self-consistently, where we again take a very simple model. We take a one-zone model, we take the electrons being injected in some profile, we just took a Gaussian in this case. We give the electrons a spherical shape, a power law in this case, and then we cool this whole thing with just synchrotron cooling in it, and we allow a sort of a nuisance parameter Doppler boosting just motivated from the gravity observations, where we have a distance from the black hole and an inclination angle that can modulate up and down the intensity of the flare. And this is what this model looks like. We have the light curve going up, we have this beautiful change in the spectral color, and then it falls down. And with this, we get this independent, non-degenerate magnetic field constraint, because again, synchrotron cooling only is dependent on the magnetic field strength. What do you think about this? Again, this was confirmed by an observation by Farah just today, who gave the talk 1 or 2, 3 weeks ago. And they published a paper 3 or 4 days before us, where they looked at the Galactic Center with NIRCam, so not in the mid infrared, but in the near infrared, and they too saw this change in spectral color in a flare. And they again modeled this with synchrotron cooling. They find 40 to 90 gauss, which by all the measures is pretty consistent with what we have.
If it's just synchrotron cooling, you have the injection and then just cool, why would you get burst?
In this case, it's the Doppler boosting.
That's what?
It's the Doppler boosting.
That's the Doppler.
That's the Doppler
And then it
boosting.
goes around, that's the opposite.
Yeah. What we don't have is, for instance, this third middle peak,
Yeah.
and you need to somehow complicate this model. So you can put in another boosting, another sort of Gaussian injection event, or you could also change the magnetic field strength. So here it's a constant over time, where you could also vary a bit, and the physics brings down the flux. But there isn't really much information that we learn from making the simple model more complicated. So this is why we just stuck with a simple mode explanation, where we have a singular injection event, and then match sort of the main feature, which is this change in the spectral index, which carries the information.
You think of something orbiting and then sudden plus burst of electrons
Yes,
in one location.
I think so. Or that's the idea behind the model.
So an action event in an orbiting tube is
That's it. That's
what would fit.
Yeah.
why would we orbit? Why not? Recognition event can be jet, can be
Yeah, we also looked at recognition events in jets, but due to the energy in the jet, that this wouldn't work out. You could not explain infrared flares for high magnetization that you expect in a jet. It would be higher energy. And
so this is the promise.
what we see in simulations is a large tube of magnetic field, more magnetized than the accretion is, that's being pushed out by an event at the jet base, and the tube gets caught by the disk, and that's what makes orbit. And then the tube disk boundary is where you get on stable, right? Have you disk pushing on it, and that can create such a path. But I mean, it's not in this model, but that is sort of
You're happy with it.
this fits our interpretation, at least at the zero stage. That's,
Yeah.
Oh, that's good.
that's
I see. So you're happy with the first.
it's a beautiful observation.
Yeah, and I think for this model, we sort of screw down the Doppler boosting, right? But it's motivated from the gravity observations that sort of track the astrometry and the polarization modulation.
So this is near the event horizon?
The time scale that you get out here is on the order of, say, 6 RG Keplerian orbits, or more in but yeah, I think that's the. Oh no, it's not the end of the talk. This actually was part of a multi-wavelength simultaneous flare as well. So we had simultaneous observations in the X-ray with Chandra and New Star. Neither of them saw anything, so there was no X-ray counterpart to this, which is a bit sad, of course, but at the other time it does constrain our maximum Lorentz factor because we need to cut off the electron distribution so that we don't have inhibition in the X-ray.
There's also no radio.
There is radio. So we had simultaneously another observation of the SMA. Because it was part of the HT observation campaign, but the HT didn't observe interferometrically, it just was like sort of a long BLB a day. We still had the SMA look at the galactic center simultaneously. This is the light curve. You do see this little blob here that happens simultaneously. Now, this little blob is on the order of over 3 Janti, which, if you look at the kind of canonical variation of the superindicator light curve, is like a 1 sigma fluctuation. So there is not really a way to say whether those two are temporally correlated. Statistically, it's perfectly by chance, would be fine as well. But we can take our model and we can ask what happens if we put in this assumption that those two are related. In order for there to be flux at all in the superimage, you need to set the minimum Lorentz factor of the electron distribution to order 10. The assumption is here 10 corresponds to the superlimited distribution. That means that you take an electron out of the thermal pool of electrons that are around Sagittarius star, and this typical thing that makes all the other superlimited variation, and then you accelerate that electron into our normal distribution. And that puts the gamma min to sort of the peak of the electron distribution, which is exactly at 10. In order to get enough flux to sort of match this function, you then constrain the number density in the emission zone to 10 to the 7. Now 10 to the 7 corresponds to roughly the estimates of the number density around Sagittarius star. So this is a consistent number. So both gamma min and 10 to the 7 sort of makes sense from the canonical assumption that you can make about the electrons around Sagittarius star. On the other hand, if you do not want any temporal correlation, this either forces you to take the electrons not from gamma min of 10, but some higher number, so if you put it to 100, and then those electron distributions have like the around Sagittarius star electron distribution, and the accelerated electron distribution does not correspond with each other, or you constrain the number density to below 10 to the 5, and then this model flux falls below the error bars on the data, and you just say, well, all the variability has nothing to do with the solution. And yeah, that's it.
Fantastic. Do we have any questions in the room?
I do have a question about the two disks. I've never heard about it. What about the mass budget in those two rings?
The mass budget.
Mass, not this, yeah, sorry, the stars.
Sorry, I just made this up.
You find the right amount.
Oh, okay. Everything's closing up. Yeah, so I'll just answer it like this. So what we can do, and what I've done but not published yet, is to take the luminosity distribution, the K-band luminosity function of the stars in each of the features, and then you sort of model them with a 6 billion years starburst. And that way, for each of the features, you get around a mass of 10 to the 4 solar masses. So all of the disks, sort of everything together, is on the order of a couple of 10 to the 4 solar masses.
It's much bigger area then. The one on the outside,
It's,
that ring, second ring on the outside.
Yeah.
Contains much bigger area.
well, it's just a number count, right?
Right,
Just
so
use-
200 contains the same number of stars.
Yeah. Well, maybe there's a reason they didn't publish it yet, but I think, yeah, from what I tried, it was around to the few times 10 to the 4 in each of the features.
Discuss with you then on physics as before.
But then if you see the numbers.
Have you reached out?
Maybe we go and ask anyone online if they have a question at all. See, already, okay, maybe I'll do this. So no one online has any questions? Oh, I think. Any last questions in the room before we call it? Nope. Okay. Thanks very much, Sebastiano. Thanks for joining.